Hello Chem 212 students, and welcome back for our second video of Chapter 1. Next we'll be continuing and finishing off the chapter on the General Chemistry Review. So after you're done, you should be ready to attempt the homework problems for this week and finally the quiz at the end of the week. So let's continue our discussion here on atomic orbitals and what happens when those when the wave functions of electrons in various atoms overlap and produce new bonding orbitals that are involved in keeping sharing electrons between atoms and keeping those atoms together. We have two electrons that are acting like a wave. This dot here represents the nucleus. When we bring these waves together, they will constructively interfere in certain places and destructively interfere in others, and the result will be various bonding orbitals. And so, for example, we have two hydrogen molecules. They get close together. Their atomic orbitals begin to overlap, and you get overlapping atomic orbitals that result in a chemical bond between the two atoms, the two hydrogen atoms. When bonds overlap, we can describe this in a couple of different ways. So we can describe with valence bond theory like this: overlapping atomic orbitals produce bonding orbitals. There is another way of describing the bonding in atoms, and that is in the production of orbitals that span the entire molecule. So this is called molecular orbital theory. And valence bond theory and molecular orbital theory are two different bonding theories that are complementary to one another, because they both explain the aspects of bonding in different ways that each complement one another. Neither one is perfectly right, but they're both a good way of describing bonding for different purposes. I'd say molecular orbital theory is a little bit more right than valence bond theory, or more useful, I'd say. But yeah, so the idea in molecular orbital theory is that when you have two individual atomic orbitals, once the molecule comes together, those atomic orbitals are then converted into entire molecules that span the entire molecule. And generally, if we have a very simple bonding arrangement like this with hydrogen, it will have two molecular orbitals: a bonding molecular orbital and an anti-bonding molecular orbital. In terms of electrons, one electron comes from one of the hydrogen atoms, the other comes from the other, and then those two electrons occupy the lower energy bonding molecular orbital in the H2 molecule, as opposed to the anti-bonding molecular orbital. And as I said, molecular orbital theory is a bit more complete of a theory compared to valence bond theory, and we'll make use of it later, especially when we're trying to see where electrons are moving in an entire molecule when they are so-called delocalized, or when the electrons can more freely move around a molecule, which does occur in certain situations. The number of molecular orbitals created is equal to the number of atomic orbitals that are used. So these two atomic orbitals created two molecular orbitals, the bonding orbital and the anti-bonding orbital. If we had a helium molecule, so imagine that we were going to make a helium molecule, we can see that a hydrogen molecule is made from two hydrogen atoms with two electrons occupying a bonding molecular orbital. If we had helium, how would the situation be different? Well, with helium, this is for hydrogen, but if we had helium, so let's do an experiment here with helium. So helium is in group 2, or in the noble gas group, but it has two valence electrons. So there would be an extra electron here and an extra electron here. And so we would have two more electrons, and those additional two electrons would have to go in the anti-bonding orbital. So molecular orbital theory here explains why helium does not tend to make bonds with itself, whereas hydrogen does. So hydrogen will make H2, which is, hydrogen bonding to hydrogen. That will occur because only these two electrons exist in that molecule, because each hydrogen has one valence electron, the one that was originally drawn. With helium, there are two. and so there will be 2 in the antibonding molecular orbital as well. And so the result is that the bonding and the antibonding cancel each other out essentially, and there's no energetic motivation to bond. It will be unstable. That's the word. The bond would be chemically unstable. If you have more complicated molecules, the bonding orbitals become more, or the molecular orbitals become more and more complicated. So you can see here are 2 molecular orbitals exhibited for the molecule CH3Br, the bromine atom being right here in this picture, bromine atom being right here. And so we'll begin to talk about the regions of electron density that occur and where that the electrons can move around. That's going to be a really, really important use of molecular orbital theory later. You don't need to understand details. These were computed by a computer, determined by a fancy quantum mechanical calculation. They can also be confirmed by spectroscopy, meaning experiments where you shoot light at molecules and see the way the light is absorbed by the interaction with electrons. Yeah, the math behind it is pretty complicated, but there will be some uses for describing certain bonding situations using molecular orbital theory in this class. So, in going back to valence bond theory, so when we talk about molecular orbital theory, we talk about orbitals spanning the entire molecule. When we talk about valence bond theory, we're talking about the overlap of atomic orbitals in order to ultimately produce, or the mixing of atomic orbitals to ultimately produce equivalent bonding orbitals, and the number of those depending on the number of electrons surrounding the atom, so, or the valence basically, or what's going to be called the steric number actually by your textbook. If we want, for example, bonding in methane, that's a bond between hydrogen and carbon. And so there's going to have to be some type of sharing of electrons that occurs between the hydrogen and the carbon, and it's happening in particular directions. In orbitals that are all equivalent, we can tell because when we look at the molecule closely with, again, spectroscopy measurements, shooting light at the molecule and see how the electrons absorb it, we can see that all of these bonds are equivalent. No bond is different than any other, so there must be 4 equivalent bonding orbitals in order to produce these. So what occurs is a so-called sp3 bonding. And the way we analyze this is by looking at the center atom, which is the carbon. The carbon has 6 electrons total, 4 valence electrons. So carbon is atom number 6. It has 6 electrons. The first 2 go in the 1s orbital, the next one in the 2s. And then if these are going to hybridize, so normally we would have the next electron would be right here. And in carbon, this one wouldn't be here. But since these are going to all be equivalent orbitals, what's going to happen is they're all going to get in their own orbital while these separate orbitals are being made. And that will leave one space for another electron that can be shared with the hydrogen atom. So when the carbon is bonding, the s orbital and the p orbitals mix or hybridize, and you create 4 individual orbitals that are all the same energy, that's somewhere between the energy of the 2s and the 2p orbital. The 1s orbital is not involved. Only the valence electrons are involved. So those are the electrons that are in the highest energy level. So in this case, that would be energy level 2. So all those electrons in the second energy level, they occupy, and those are the 4 valence electrons in carbon. They occupy the 4 sp3 orbitals that were produced from 1 s orbital and 3 p orbitals. At that point, you have 4 equal orbitals that can be involved in the bonding. These orbitals look like this. They're somewhat shaped like a p orbital, but they have a larger lobe on one side than the other. And the larger lobe is where the overlap is going to occur and the bonding. So if we look at the carbon now, it has 4 equivalent bonding orbitals, hybridized bonding orbitals. Now the blue lobes are here. They're kind of overlapping with the red lobes on the opposite side, but we're not going to draw them just for the sake of clarity. So we're only drawing the red side here. And these are arranged as far away in 3D space as they can be from one another. Since there's 4 of them, that's in a so-called tetrahedral arrangement, where all of the angles are 109.5 here between the center of these. Then the hydrogen, so this is this is an sp3 bonding orbital. I'm going to use blue now. This is one sp3 bonding orbital. This is another. This is another. And this is another. And then this is the hydrogen atom's 1s orbital. 1s, 1s, 1s. And when those overlap, that creates a bond. And this is the essence of valence bond theory. But the idea is that the carbon atom itself does not have 4 equivalent bonding orbitals, but the 1s orbital and the 3p orbitals, both in the second energy level, hybridize to create 4 equivalent bonding orbitals. So what if we were doing this for water? Well, if we draw a Lewis structure for water, it's oxygen. We know oxygen likes to make 2 bonds and have 2 lone pairs. We could do this the long old-fashioned way, or we can just recognize that H2O here, it's oxygen making 2 bonds, 1 to each hydrogen, and then it has 2 lone pairs here. So when it comes to oxygen, oxygen is in group 6. It has 6 valence electrons, 8 electrons total. And so those electrons, there's 8 total. So the first 2 go into the 1s orbital, and then the next ones here, it would be like this, and then like this. So 1, 2, 3, 4, 5, 6, 7, 8. And out of those 8, 6 are valence electrons. These 6 in this orbital, these orbitals. So these are going to hybridize, and they're going to make 4 equivalent orbitals, because there's got to be 4 orbitals, 2 for the bonds and 2 for the lone pairs. Okay, so we're going to have 4 equivalent hybridized orbitals, and the electrons, there are 6 of them. So what's going to happen is there will be 2 that are filled up. These are right here the lone pairs. So these are going to be the ones containing the lone pairs, and these are going to be the bonding orbitals. And altogether we have 4 sp3 orbitals. And so when it comes to the oxygen, we're going to be drawing 4 sp3 orbitals, all arranged in the 109.5 degree arrangement here. This is tetrahedral. Tetrahedral electrons. But the bond itself is going to be bent, or the molecule itself is going to be bent in shape, because in here we'll have 2 lone pairs, and then here we'll have the hydrogen 1s orbital. So this is a hydrogen 1s orbital overlapping. This is a hydrogen 1s, hydrogen 1s, and then this is the carbon 3p a carbon sp3 rather. Right there. And there are 2 electrons in here too being shared. So they're being shared right here in the overlap. Would have drawn a little bit bigger of an overlap here. But yeah, there'll be 2 electrons in here. 2 electrons. Might be a little bit difficult to see. I'll draw it a little farther out. So this is 1 electron, this is the other. Sorry about that. But there are 2 electrons here being shared. 1 from the oxygen and 1 from the hydrogen. So these are the ones from the oxygen, the other ones from the hydrogen. Now, so those were 2 examples of sp3 hybridization. So those where we had a total of 4 bonds and 4 lone pairs. You'll get sp3 hybridization. If you have 2 bonds, or sorry, here we have 2 bonding directions, basically, and no lone pairs. We get 3 hybridized orbitals. So again, going back, here we have 4 bonded atoms. And so there's going to be 4 places for the electrons to go. That's why we need 1 s orbital and 3 p's. In case of water, 2 of the orbitals are lone pairs, or containing lone pairs, and 2 are bonded atoms. So again, we got 4 directions where we're going. 2 are in lone pairs, and 2 are bonded atoms. But in the case of ethene here, we have 3 bonded atoms and no lone pairs. And so essentially the bonding is going out in 3 directions. The electrons are going out in 3 directions. 2 of those are to the hydrogen, 1 is to the other carbon. So this is going to involve sp2 hybridization. 1 p orbital will not be used because we only need to bond in 3 equivalent directions. So we're going to take 1 s orbital and 2 p orbitals, and those will be hybridized, and they contain the 3 electrons. That leaves 1 electron left in the 2p orbital that was not hybridized. So in this case, why is this different from the previous ones? It's because we only have 3 bonded atoms and no lone pairs. So we have electrons going in 3 directions instead of 4. And so only 3 orbitals are needed to do this. So when you have sp2 hybridization, you have orbitals, sp2 hybridized orbitals going out in 3 directions. They are all 120 degrees from each other in a flat arrangement. And there's 1 p orbital left, which is indicated here by the red and the blue lobes. So the gray ones are the hybridized orbitals, and the red and the blue are the p atomic orbital remaining on the carbon. So when the valence bond theory bonding happens, when the overlap between the hybridized orbitals, we've got 3 hybridized orbitals on the carbon. 2 of those overlap with the hydrogen atomic orbitals to create so-called sigma bonds. So always the overlap is what's called a sigma bond when you have a head-on overlap. So all the previous bonds we talked about too were sigma bonds as well. And so we've got an overlap here between the 2 bonding orbitals, the remaining bonding orbitals between the carbon atoms. And we still got this 1 electron left in the p orbital in the carbon atoms. And this is how a double bond is formed. A double bond is a different kind of bond than a single bond. A single bond only involves a sigma bond, but a double bond is going to involve a sigma bond with direct overlap and a sideways bond between the 2 atomic orbitals. So this sideways bond is referred to as a pi bond. It's the sideways overlap of 2 remaining atomic orbitals after the other orbitals have been turned into hybrid orbitals. And so when we have a double bond like this, notice a double bond. So a double bond. Double bond equals 1 sigma bond and 1 pi bond. And a triple bond is one sigma bond, and two pi bonds. So if we have, for example, carbon double bond to carbon, there'll be two p orbitals remaining, one vertical and one coming out of the page in that case. And so that would result in two sideways overlaps. And this is valence bond theory. So again, a single bond here is a single bond is called a sigma bond. A double bond is composed of a sigma bond and a pi bond. A triple bond is composed of a sigma bond and two pi bonds. So as we saw in the example here with ethene, pi bonds are formed by the sideways overlap of p orbitals, and the result is both constructive and destructive interference. Again, as I said, molecular orbital theory is complementary to valence bond theories. They each describe the same thing, but in different ways with different strengths and weaknesses. And so, for example, here in the pi bond we saw here, there's a sideways overlap of two p orbitals. If those were represented as bonding and anti-bonding molecular orbitals, we would get two molecular orbitals from the two p orbitals, the ones that were left over, the ones that weren't hybridized, and the two electrons would go into the bonding orbital, pi bonding orbital, and would form a bond. And so this is a molecular orbital description of why it is that some atoms will be apt to form pi bonds or double or triple bonds in certain situations, and others won't. So this is the molecular orbital description. Again, we're going to come and talk about molecular orbitals later on in the class when they become more relevant. They're especially relevant when electrons move around a lot in a molecule. But for now, it's enough to know that there's two different ways of describing the bonding, either with valence bond theory, which is quite a bit more intuitive, and but also molecular orbital theory is possible. Again, you're not supposed to be able to figure out what these shapes are. These are figured out by complicated calculations on a computer. Finally, we have acetylene or ethylene. This carbon here is involved with one bond to a carbon atom, one bond to a hydrogen atom. So two bonded atoms and no lone pairs. So you need two equivalent bonding orbitals. And so the hybridization is going to be sp, one s orbital and one p orbital to collect two orbitals. And so again, carbon has 4 valence electrons. We spread them out for the purposes of the production of the hybridization of the orbitals. So 2 of the electrons are in the hybridized sp orbitals, formed from one s orbital and one p orbital, and 2 are in the 2p orbitals for this carbon. And so the result is that we get 2 hybridized bonding orbitals, which are positioned exactly opposite one another as far as ways they can be from one another. And so these are the sp orbitals of the carbon atoms overlapping with the 1s atomic orbital of the hydrogen atom. Then there are 2 p orbitals remaining, each with a single electron, and those involve a sideways bonding interaction, the so-called pi bond. And so this is a triple bond with 1 sigma bond and 2 pi bonds. In terms of the characteristics of the molecules, triple bonds are generally the strongest and the shortest. So you can see they have the strongest bond energy, or energy required to break the bond, and they have the shortest distance. This carbon-carbon triple bond here. Carbon-carbon double bond is weaker than the triple bond and longer. And then the single bond is the longest and the weakest of the 3 bonds. And so that's an important trend to keep in mind, is that triple bonds are generally stronger and shorter than double bonds, which are generally stronger and shorter than single bonds. So the way to determine the hybridization and everything else is to look at the number of sigma bonds, or the number of bonded atoms, and the number of lone pairs. So the number of sigma bonds is the number of atoms bonded, because A double or triple bond will involve one single bond, sigma bond. It's not the pi bonds we're counting. It's just how many atoms are bonded. Each bonded atom will give you one sigma bond. And the number of lone pairs is also important. These add up to what's referred to as the steric number. So if the steric number here is 4, like we can see for methane, for NH3, for water, they all have a total of 3 bonded atoms and four total bonded atoms and lone pair added together. For this carbon, it's four bonded atoms, no lone pairs. For this nitrogen, it's 3 bonded atoms, 1 lone pair. For oxygen, it's 2 bonded atoms and 2 lone pairs. And so these together add to 4. So these will all be sp3 hybridized, sp3, because they need 4 equivalent bonding orbitals. So in valence bond theory, they'll be sp3 hybridized. Their electron geometry will be tetrahedral. So if we want to determine the molecular geometry, we determine the steric number. If the steric number is 4, then the hybridization is sp3. The steric number is 3, then the hybridization is sp2. Steric number is 2, then it's sp. And it's just enough orbitals to to take care of everything that's happening in the bonding of the molecule. So these all have steric number 4, so they're all sp3 hybridized. So here we have methane, the CH4, 4 equal bonds, they're all equal angles, 109.5. When the steric number is 4, your bond angles are going to be around 109.5. You can see that it's a little smaller for NH3 because its steric number is 4, but the lone pair takes up a little bit more space. And then for water, the bonding angle is a little bit shorter than 109.5, and it's because having lone pairs takes up a little bit of the extra space, and it pushes the hydrogens a little bit closer together. But the electron group geometry is called tetrahedral. The shape of the molecule may have different names because we don't count the lone pair when we talk about the shape of the molecule, the geometry. So here the first examples, all with steric number 4. They have sp3 hybridization. Their electron pair arrangement is tetrahedral, but their shapes don't include the electron pair. So it's for NH3, it's trigonal pyramidal. So the NH3 right here, everything minus the top. So it's tetrahedral on the bottom, like the CH4, but it's got a lone pair on the top. So it's like a tripod. Call it trigonal pyramidal. For water, right here, we can see it's tetrahedral if we include the lone pairs, but if we just take into account the arrangement of the atoms of the molecular geometry, it's this bent or angular shape. So to determine the geometry, count the number of bonded atoms and the number of lone pairs, add them together, you get the steric number. If the steric number is 4 and there's no lone pairs, it's tetrahedral. Steric number is 4 and there's 1 lone pair, it's trigonal pyramidal. Steric number is 4 and there's 2 lone pairs, it's bent. Now there are some exceptions to the octet rule. One example is BF3. So boron is an exception in that it does not need to have 6 electrons around it. It can get by, it does not need to have 8. It can get by with 6 with just 3 bonds. And so it's an exception to the octet rule. It has here 3 bonded atoms, no lone pairs. So its steric number is 3. 3 bonded atoms is plus 0 lone pairs. So it's sp2 hybridized, meaning that the angles are 120 degrees away from each other. And this geometry is called trigonal planar. Trigonal planar with BF3. BeH2 is another exception. So BeH2, Be is the 4th element. It only has 2 valence electrons. It's in group 2, and so it tends to just make 1 bond with hydrogen, and that's it. Because the beryllium has 2 valence electrons, the hydrogen has 2. That's a total of 4. Once it makes this bond, it's done. And so here the number of bonded atoms is 2. So 2 sigma bonds and 0 lone pairs plus 0. So that's steric number is 2. And so the hybridization is sp3, sp2, or sorry, sp, one s orbital, one p orbital, to make 2 equivalent bonding orbitals. And then finally, what the result is that these will be exactly across from each other, and this is going to be linear. So when the hybridization is sp like this, you end up with a linear arrangement. CO2 is a similar but different situation. So we know carbon likes to make 4 bonds and oxygen likes to make 2. So we could probably pretty quickly figure out that this is going to be carbon making 4 bonds here. Oxygen generally makes 2 with 2 lone pairs. And so that's, now we're kind of using the shortcut method for drawing Lewis structures. Notice it's a lot simpler. Again, here we have 2 sigma bonds. 2 atoms that are bonded. There are also 2 pi bonds, but we don't care about those for the purposes of determining the shape. And then on the carbon, so again, the shape is determined around the carbon. There are 0 lone pairs on the carbon. Yes, there are lone pairs on the outside atoms, but we count the shape as being around the center atom. So the steric number for this carbon is 2. And so again, the hybridization would be sp, and this would also be linear. When the hybridization is sp, either in this special case with beryllium or in a case like this with carbon dioxide with 2 sigma bonds but no lone pairs in the carbon, the shape will be linear. And so that's how we determine the hybridization and the bonding. To summarize, if the steric number is 4 and it's sp3, then if there's no lone pairs, it's tetrahedral. If there's 1 lone pair, it's trigonal pyramidal. And if there's 2 lone pairs, it is bent in shape. If the steric number is 3, it's sp2 hybridized. If you have 1 lone pair, it's bent. If you have no lone pairs, it's trigonal planar. Finally, if the steric number is 2, it's sp hybridized, and it has a linear shape. Finally, what's the purpose of figuring out all these molecular geometries and whether bonds are polar? It's because we want to know if the molecule overall is polar. Now, we did this in the past. We could figure out if a molecule is polar is based on the symmetry of the molecule, the shape, and also whether it has any polar bonds. In this class, we're going to be not only concerned with whether a molecule is polar or not, but how polar is it? And the how polar is it can be looked up and determined with a measurement called the dipole moment. And so the dipole moment has units of debye, where a debye is 10 to the minus 18th ESU times centimeters. We'll talk about how to calculate a dipole moment. I won't ask you to calculate dipole moments, but you may be asked to look them up as a part of lab assignments. So ESU is a unit of charge. 1 electron has a charge of 4.8 times 10 to the minus 10 ESU. And centimeters are a distance, a measurement of distance. And so this is the way the dipole moment unit is defined. A kind of strange definition, admittedly. And again, you don't need to be able to calculate these. We'll just be looking them up. So this is to give you an example. If you look up a dipole moment, how it was calculated. So if we have chloromethane here, so in chloromethane, the charge here on the chlorine is so we plug in the charge. It's 1.056 times 10 to the minus 10 ESU. And so this is the amount of charge separation, basically the difference in the charge here, the amount of electrons here, and the chlorine, and the amount near the carbon. And the distance of separation being 1.772 times 10 to the minus 8 centimeters, which is the distance here. And if we multiply these and convert, we get 1.87 debye. And so this is the way in which these dipole moments that you might calculate, that might look up later online, will be calculated in a molecule. A couple of other examples here for various different bonds: carbon to oxygen, oxygen to hydrogen, carbon to oxygen. So you can see here that with carbon and oxygen double bond, you end up with a more higher Debye, or difference in separation, difference in charge, than you did with a single bond or OH here, due to the presence of the additional electrons in the double bond. Again, you do not need to know how to calculate these. These are just simply to show you this is how these Debyes that you might be looking up are calculated. Don't worry too much about the math here. Now, when we're deciding how polar we think a molecule is, if we're not looking up the dipole moment in Debye's, we can have a pretty good guess if we look at the shapes of the molecules and whether there's polar bonds or not. So, for example, we have this molecule which is called dichloromethane. The electronegativity of chlorine, if you go and look it up, is about 3. It's a little bit more than 3, I think, but let's say it's about 3. And for carbon, it's about 2.5. So this difference is at least 0.5. And it's in the favor of the chlorine. So this is a tetrahedral arrangement, 4 bonded atoms, no lone pairs in the carbon, and the electrons are being pulled more to one side than the other. So there's a so-called net molecular dipole moment, which is what is attempting to be shown with the unit Debye for the overall molecule. This overall net dipole moment, though, is just going to mean pull of electrons towards the chlorine. So this side of the molecule will be partially negative due to the additional electron charge, and this one will be partially positive. A similar situation occurs with ammonia, which is trigonal pyramidal. It's got a tetrahedral electron arrangement, but the top electrons here are a lone pair. And so the net dipole moment is up towards the nitrogen, because the nitrogen has an electronegativity of about 3.0. So the nitrogen has an electronegativity about 3.0, and it's about 2.1 for hydrogen. And so that's a pretty big difference, 0.9. And so the electrons are pulled more towards the nitrogen. And then finally, with water, it's got this bent shape. Again, the oxygen here, an electronegativity of 3.5. For hydrogen, it's 2.1. And so a huge difference in electronegativity. The electrons are really pulled towards the oxygen side of this bent water molecule. So what's important is you have to determine the molecule's geometry first before you can determine the polarity. So you should draw a Lewis structure, determine the geometry. The geometry must be asymmetrical in order for the molecule to be polar, and there also must be polar bonds. If the geometry of the molecule is completely symmetrical, there will be no net dipole moment. It has to be different on one side than it is on the other. For example, if there were more hydrogens on the other side of that oxygen there, well, then there would be something it would be the same all the way around. And so you have to have a asymmetrical shape like this trigonal planar, or this bent, or at least different atoms on each side, like we had here with different atoms with the chlorine than the hydrogen, to have a net dipole moment. So a molecular polarity can be inferred in the way we did there by considering the polarity of the bonds and the molecular shape. It can also be mapped out in a so-called electrostatic potential map. And so a really useful way of doing that, which I'll be using later, I'm going to show you guys for a moment right now. We can use handheld models, which I recommended to you for purchase. If you want, you can also use these virtual models like this. So here, if we go to moleview.org, and there's a link in the syllabus as well to this, we can go here, and this is for caffeine. We can look at the MEP surface. Right here, MEP surface loosened, and we can see that same type of arrangement. We can see like where the oxygens are, which are very high in electronegativity, it's red, indicating electron density, and where electron density is lacking, it's blue, like over here, away from the nitrogen pulling electrons away there. So that's a more accurate and complete way of seeing the electron density. Here we can see that it's high around the chlorine. And so here's some dipole moments for various molecules. You can see acetone here with this carbon-oxygen bond, very negative around the oxygen. So here it would be pretty negative here around the oxygen, and then pretty positive over here opposite the oxygen. So it has a large dipole moment. Chloromethane that we saw earlier is pretty big. Water. These have very polar bonds and are asymmetrical. And then, for example, carbon tetrachloride, which is tetrahedral with chlorine all the way around in every direction, although each of these bonds is polar, because they're all symmetrically arranged in a tetrahedral arrangement, they all have poles on electrons that are opposing one another perfectly. And so they cancel each other out and have no net dipole. Also, carbon-hydrogen bonds are very nonpolar, so we can see that a molecule with all carbon and hydrogen bonds is pretty nonpolar. Finally, the polarities of these molecules, or the lack of polarity, can result in various types of intermolecular forces. And so these include dipole-dipole interactions, hydrogen bonding, or dispersion forces, which are primarily important in large molecules or in nonpolar molecules. So when a molecule is polar, when you have a polar molecule like the acetone we saw earlier, it's going to have a more negative side. Here, the negative side closer to the oxygen, which pulls electrons away from the carbon. And it's going to have a more positive side. So the negative side of one molecule will be attracted to the positive side of a neighboring molecule. And so you can get pretty strong attractions between these. And so the result is that acetone, for example, is a liquid at room temperature and not a gas, because the molecules are fairly attracted to each other due to these dipole-dipole intermolecular forces. The result is higher boiling points and melting points because the molecules stick together, so it's harder to disrupt them and have them fly away from each other and boil, for example. So here's a couple of other examples. So we can see for isobutylene here compared to acetone, notice it has no oxygen atom. It only has nonpolar carbon-carbon, carbon-hydrogen bonds. Very nonpolar. So it does not have dipole-dipole forces. And so the melting points and the boiling points are very low. It will be a gas at room temperature. However, the acetone is a polar molecule. You can see here, especially this bond right here, very polar. It's trigonal planar around this carbon, and electrons are being pulled towards the oxygen. Boiling point is much higher for acetone due to these stronger dipole-dipole forces. Hydrogen bonds. Hydrogen bonds are an especially strong type of dipole-dipole attraction. So hydrogen bonds are strong because they're basically they come from very, very polar molecules. The electronegativity difference between hydrogen, oxygen, and hydrogen and nitrogen is very high. And so when we have bonds with oxygen to hydrogen or nitrogen to hydrogen, they result in very, very polar bonds, which can lead to very, very polar molecules. So here we can see in water, we have this bent shape for water. It's got two bonded atoms, two lone pairs, so that results in a bent shape. And it has extremely polar bonds where the oxygen is really pulling the electrons towards itself. And so the result is that the oxygen side has a significant partial negative charge, and the hydrogen side has a significant partial positive charge. And so they're attracted to one another. And then the similar situation happens with nitrogen, not as strong because the nitrogen is less electronegative than the oxygen, but this is trigonal pyramidal. And as we've seen before, the electrons all get pulled towards the nitrogen in this molecule, which is not symmetrical. The top here in the trigonal planar molecule is different from the bottom. And so the electrons are all going towards the nitrogen. And so the nitrogen side of the molecule is more negative, and the opposite side where the hydrogens are is more positive. And because these have especially big differences in electronegativity, they make especially strong bonds. Intermolecular forces. So when you have hydrogen bonded to oxygen, nitrogen, or fluorine, you have a molecule that can participate in hydrogen bonding. So the partial positive charge will go on the hydrogen atom attached to the nitrogen, oxygen, or fluorine. The partial negative charge will be nearer to the oxygen, the nitrogen, or the fluorine. So it's important to note that hydrogen bonds are not chemical bonds. They're not covalent bonds. They're not ionic bonds. They're much weaker than chemical bonds. But they are quite strong in terms of intermolecular forces. They're particularly strong dipole-dipole forces. All right, and this word protic, we're going to come back to this, but sometimes these types of molecules here with oxygen-hydrogen bonds are called protic. We'll talk about that term later in the textbook. In terms of hydrogen bonding, so you can see here, for triethylamine, there's no hydrogen bonding because the nitrogen is not directly attached to a hydrogen. But there is hydrogen bonding for ethylamine, ethylmethylamine, because there is a bond between nitrogen and hydrogen. And so you get hydrogen bonding occurring. You can see the result in the boiling point. The boiling point is higher because the attraction between the molecules is stronger. And finally, propylamine here, all the same number of carbons and nitrogen and hydrogens, but this one has a much higher boiling point because it has even more hydrogen bonding. And side note about hydrogen bonds that you'll learn more about later in Chem 213 is hydrogen bonds that actually keep the two strands of the double-stranded DNA alpha helix together. And so they're strong enough to keep it together, but also weak enough that it can be unwrapped. So these hydrogen bonds are really key to the structure of DNA. So finally, we'll talk about London dispersion forces. So if two molecules are completely nonpolar, will they attract one another? The answer is yes, but the how is different because nonpolar molecules have their electrons spread out pretty evenly. And so they're not particularly negative or positive in one particular place. However, the electrons are constantly moving around in their molecular orbitals. So it is possible that just by random chance, there will be more electrons on one side of the molecule than on the other for just a moment. And the result is that you get, just for a split fraction of a second, a negative side to one molecule and a positive side to the neighboring molecule. This happens in polar molecules too, although the forces only become large when the molecules get really big. And so the uneven distribution of electrons produces a temporary dipole, which can induce a temporary dipole in the neighboring molecule. And then there'll be some attraction, negative, positive here. So these attractions, because they're fleeting, they don't last long, they're generally weak. But if there's a lot of it, they can add up and they can become quite significant. So that's why you can, for much larger molecules, often they'll be solid even if they're nonpolar. We're talking about or they'll be liquid. We're talking about like oils or fats. These are nonpolar molecules that are big a lot of the times, and so their London dispersion forces can be big enough to cause them to stick together pretty well and be solids or liquids. The greater the surface area of the molecule, the longer it is, the bigger it is, the greater the London dispersion forces. And it just so happens that London dispersion forces are what are responsible for helping a gecko stick to things. So you can see here, as a molecule gets bigger, it has higher boiling points. These are all non-polar molecules due to the fact that carbon-hydrogen bonds are not polar, carbon-carbon bonds are not polar, so they have no polar bonds. They're not polar, but their London dispersion forces do get larger and larger as the molecules get bigger. So butane is like in your lighter. When you flip the switch, it comes out as a gas. But hexane is a liquid, and it's you can find some hexane in your gasoline, for example. Not much. It's usually larger ones in your gasoline, but hexane is a liquid at room temperature. It has a higher boiling point. Also, the shape of the molecule matters. The longer the molecule, the more surface area it will have. So the stronger the London dispersion forces there will be. You can see that here with pentane, as opposed to this so-called 2-methylbutane. You'll learn how to name these later. Which is not as long and spread out, so it doesn't have as much of this London dispersion force, resulting in a lower boiling point. This 2,2-dimethylpropane has the least surface area, so it has the lowest boiling point. Finally, in terms of solubility, one important reason why we care so much about intermolecular forces in organic chemistry is because we want to know what molecules will mix with what other molecules, what is soluble and what. And the rule for solubility is like dissolves like. So polar compounds mix well with other polar compounds. So for example, if you have two molecules that are both capable of hydrogen bonding and have similar intermolecular forces, they would mix. Nonpolar compounds generally mix well with other nonpolar compounds. So you've probably heard oil and water don't mix. Oil is generally nonpolar, water is polar. So water mixes very great with ethanol, for example. So this is water. It's got hydrogen bonding. And then this is ethanol. I'll use the organic structure here. So you can see that they both have hydrogen bonding because they both have OH. And also the nonpolar hydrocarbon part for methanol is not so big. So they both have OH bonds. So they can hydrogen bond to one another. So they mix very well. However, nonpolar substances will not mix as well. They'll only mix with other nonpolar substances. So, oils will mix with other oils, but not with water. So here's an example of an oil molecule. So it does have a polar part at the end, but it's a very long nonpolar part. So often the nonpolar part is called hydrophobic. You can tell this part is nonpolar because it only has nonpolar carbon-hydrogen, carbon-carbon bonds. This has very polar carbon and oxygen bonds, but because the nonpolar part is so large, overall this is nonpolar, but it has a polar part. So this is an example of what's called a emulsifier molecule, like soap. This is a soap molecule. And so we use these types of molecules to help to bind together polar and nonpolar molecules. The nonpolar oils, grease, and dirt will bind to the nonpolar part of the molecule, and the polar part can bond to water. The result is that you can get a micelle like this. This is a so-called micelle is the word. And so the nonpolar part of the molecule will be attracted to the oil. The polar part will be attracted to water. So if water's out here, then this polar part will be attracted to the water, and so we'll face out towards the water. And this is the way that oil is washed away. So we're going to be using these ideas of polarity that we built up, bonding and polarity, as we move forward in our OChem class. So these important ideas that you learned in GChem will continue to be important to you as you move into OChem. I know this video is a little longer than I'd hoped, if you sorry about that. I'll give you guys a little extra time if you need it. Just talk to me. But I think that should be able to watch the videos and complete the homework assignment this week, as yeah, after you watch the video. And I thank you for listening, and I look forward to seeing you guys in lab. All right, have a good one.